We're going to graph the same thing that you graphed yesterday, and then we're going to mark some important information about it, and then we're going to learn how to find these things using the ideas that you guys just did on the board. So by factoring and figuring out where certain things are equal to 0, we're going to be able to find these different things that are listed here. Okay? All right, and don't mind the microphone. I know it doesn't project my voice. It's just recording, so if people are absent, they can watch the notes. Okay. So when you graph y equals 1 over x, what you should have seen is that the graph did not go right here at all. Okay, so when we graph by hand, I know your calculator didn't do this, but we're going to mark that with a dashed line. And what that's telling us is this is an asymptote. This is kind of a boundary that the graph will follow. And vertical asymptotes, so vertical lines like this, the graph does not cross. Okay? Horizontal ones, sometimes it crosses and sometimes it doesn't. We'll talk about that. But you guys also had this idea that it didn't cross here. Okay? And if you plugged in a couple points, which you guys got from the table, so I told you how to go into your calculator, right, and look at the table of values, and you guys could quickly fill those in. If you plotted all those points, you got something like this. So if I plug in 1, I get 1. If I plug in 2, I get a half. So I get some sort of curve like this. So the curve gets closer and closer and closer to the asymptotes, but never crosses them. How many of you guys feel pretty familiar with the idea of asymptotes from Algebra 2? How many of you guys feel like I'm talking about a word that you have no idea what it is? Okay, so basically, let me draw the other one, and we'll talk a little bit more about what it is. When I plug in -1, I get -1, and when I plug in -2, I get -1/2. And when I say plug in, I'm talking about plugging into this function that we're graphing, y equals 1 over x. So we get a graph that looks like this. How many of your graphs looked like those 2 branches on your calculator, something like that? Okay. So basically what's happening here, if this was one of the problems on the back side of the paper, you wouldn't need to simplify it, right? It doesn't need factoring or anything like that. What would be the x values when this function would be undefined? So when would the denominator be equal to 0? When x was equal to what? 0, okay, right? If you plugged 0 in for x, you'd get a 0 in the denominator. Does everybody see that? Okay? That's why this asymptote is here. Okay? That asymptote is there because you literally cannot plug in 0 for x. There is no way to do the calculation. So these vertical asymptotes are marking the spots on our graph where we can't plug that number in because we can't get an answer when we do plug it in. Okay? So this graph has a vertical asymptote at x equals 0. So vertical lines have the equation x equals and whatever number they're crossing through. This is also the same thing you would get if you listed the undefined values of the equation, right, at x equals 0, like we just did up on the board with all the things we simplified. Okay? This graph also has what we call a horizontal asymptote. So vertical asymptotes we don't cross because those are places where the graph is undefined. But notice that the graph follows them. It starts getting really close to them. Okay? And so the ends of the graph start looking just like those vertical lines. Horizontal asymptotes are a little bit different. A graph could go all around them in here. They're really to describe at the very ends of the graph what's going to happen. So basically, the fact I have a horizontal asymptote is telling me that this graph is eventually, way over here at this end, going to look like this horizontal line. If I hadn't plugged in any points, I didn't know if it was going to come from up here or down here, but eventually it's just going to kind of even out and start to look like this horizontal line. It'll never actually reach it, but it'll look like it. Okay? And then same thing on this end. So a horizontal line has the equation y equals, and whatever value it crosses through. And in this case, we're crossing through 0, okay? So on the y-axis, so it would be y equals 0. Okay? An oblique asymptote would be if we did not have the horizontal asymptote, if it was like twisted and kind of went slanted, and instead of our graphs being these nice kind of little squarish curves, they like shot off in another direction along a different line. So if you have a horizontal asymptote, and they're following a horizontal line, then they're not going to follow a slanted line. So it's like one or the other between these two. So since we have a horizontal asymptote, we don't have a different slanted line that our function follows instead. So we just say there isn't one of these, or we say none. Okay. Are there any holes in this graph? So a hole is literally a hole. It would be like you're traveling along this nice little curve, and then all of a sudden there's a little open spot right here that it just kind of jumps over and then keeps following on the curve. So there's no holes in this graph. I get that it's disconnected at certain spots, but a hole would have to be on the curve, literally an open point that you're skipping. So this graph doesn't have any holes, so we'll write none. And what about x-intercepts? Okay. Does the graph have any x-intercepts? So does the curve hit the x-axis, and you can say, oh, it hits the x-axis right here at this number? No, not at all. Okay, it doesn't have any. And that can go back to what we just talked about from your worksheet too. We said when the denominator is equal to 0, the function's undefined. That's where we're getting our vertical asymptote. So if you want to write a little note here, that's when the function was undefined. Okay? And then Alexis brought up the question about what about in the numerator? What does that stuff tell us? And we said if the numerator was equal to 0, that would be our x-intercept. But here the numerator is just 1. Is there anything you can plug in that's going to change the 1 from being a 1? No. You can change the denominator to different numbers, but the 1 in the numerator is going to stay a 1 because it doesn't have any variable with it. So you can't make it equal to 0, which means you can't get any of these. Okay? So that's why we don't have any x-intercepts in this case. All right, who thinks they would be able to identify the domain of this function? James? Good. So he says all real numbers except x cannot be equal to 0. So do you guys see that left and right, there's no boundary. The graph keeps going left or right. The problem is it skips this x value right here. We weren't allowed to put why we put the asymptote. So you can write all real numbers except x equals 0, or you can write x cannot equal 0. And if you tell me one thing it cannot be, it's implied that it can be all of the other real numbers. Okay? All right, what about the range, the y value? Someone different, can you tell us what the range of the function would be? So thinking up and down now instead of left and right. Does it have a maximum? Is there a place that it hits that it doesn't go any higher? No. Okay. Does it have a minimum? No. Okay, so it has no maximum and no minimum, which kind of wants me to say all real numbers, but then I have to say, does it have any holes or any places where the graph skips a certain y value? So is there any y value that gets skipped? At 0, right? This gets closer and closer to 0, but never hits it. And so does this one. So it's like they leave out this one thing at 0. So the same idea for the range as it is for the domain. You could write all real numbers except y equals 0, or you can just write y cannot equal 0, and I'll assume you mean it can't equal that, but it can equal everything else. Okay? Is this all right with everybody? All right, so a couple things we're going to recognize today, and then other things that we have to fill out tomorrow. So to find vertical asymptotes, we should be able to answer this question today. So I'm going to give you stuff to graph that looks like that. I know the notation is weird, but P of x over Q of x just means you're going to have some weird thing on top, right, and some weird thing on bottom, both that have x in them. Okay? That's like all the problems you simplified on the back side of the worksheet. So basically, you're going to be graphing stuff that looks like the problems on the back side of that worksheet. Okay? So how do you find the vertical asymptotes? So go back and think about what we just did. Why was this a vertical asymptote? Why did we mark that on our graph? Where did we get it from that it should be at 0? How did the equation tell us, oh, when x is equal to 0, we can't plug in the number? So what did we write down for all of your functions around the room? What did you guys identify? Besides simplifying it, you wrote, like, it can't equal. James?
What value of y squared that one is the function of the function?
Good. Okay, so everybody go to where it says vertical asymptotes. Okay? To find a vertical asymptote, you need to find the values of x. I don't have space to write that high, but I'll write it right here. Find the values of x that make the function undefined. And then some people are even going to have a hard time with that language. What do you mean make the function undefined? What makes the function undefined if it's a fraction with variables in both numerator and denominator? How are you going to make it undefined? Whatever makes the denominator equal 0, okay? So x equals some number, and this number has to be what makes the denominator equal to 0. Okay? That's kind of in more layman's term instead of using like the math terms. Basically, you're going to do what you did in all those problems. You're going to factor it. You're going to figure out what would make the denominator equal to 0. That's going to tell you where it's undefined. Besides just telling you it's undefined, that means now when you're making a graph of that thing, you put the vertical asymptotes into those spots. Okay? We didn't talk about horizontal asymptotes or oblique asymptotes yet. We're going to look at that tomorrow. They're a little more difficult and involved. Okay? What about to find the x-intercepts? We talked about this at the end after everyone's problem was up. How did we say you would find the x-intercepts of the rational function? What's it? Good. When you would get 0 in the denominator or in the numerator, okay? So when the numerator equals 0, okay? So those x values will give you x-intercepts. Now remember, in the graph that we just saw, bring this back up if you're copying it, this graph had no x-intercepts, and that was because when we looked at the function, could you make the numerator equal to 0 by changing the value of x? No, because there was no x in the numerator, so you couldn't make just the numerator equal to 0. All right? So that's why it had no x-intercepts. Okay? The last thing we're going to fill in today is like, what about this idea of holes? Okay? So basically, the holes are the factors that got canceled out. The ones that looked like they made it undefined, but they also looked like they made an x-intercept, so they made 0 in the numerator and the denominator, those are the places you would have holes. So for example, we might factor something that looks like this. Right? Where would we have vertical asymptotes for this function? So what would make the denominator equal to 0? Originally, we'd say -5 and 3, right? And then we would say we have x-intercepts at -8 and 3, but then we'd say, oh, wait, not at 3 because we already have an asymptote at 3. This factor right here that gets canceled out like that, that's what makes a hole, okay? So this function would have a hole 3. And what that means is whatever that graph ended up looking like, let's say it went like this or something, where x was equal to 3, you would go up on that graph and you would literally erase part of it and put a hole. Not on 3 on the x-axis, but on the graph when it was aligned with x equal to 3. Okay, so our graph didn't have any holes. We just graphed. It didn't have any holes because was there any factors in the numerator and the denominator that were the same that got canceled out? No. Okay? So verbally, how you would say this is basically it's the x that creates a 0 in the factors that get canceled out. So basically here you want to look for factors that cancel out. So the problems that you guys put up on the board, would they have had holes if we graphed them? Yeah. All of you guys had factors that canceled out of both numerator and denominator. Everything we put up there would have had a hole on the graph. Okay? Does that make sense? So basically, hopefully now you don't see yesterday's stuff as much as busy work. We're going to get graphs that have these different curves and follow different asymptotes. How you're going to determine what these asymptotes are, vertical ones are when the denominator is equal to 0. X-intercepts are when the numerator is equal to 0. And holes are the factors that cancel out. Does that make sense to everybody for now? Tomorrow we're going to look at a big chart of values, but I'm going to fill the chart in for you because it's kind of a waste of time for you guys to fill in all the values. And you're going to look for patterns, and those patterns are going to help us make some decisions about horizontal and oblique asymptotes. Okay? They're a little more complicated and a little harder to deal with. Okay?